My name is Michael Lentine. I'm the Director of Physics Engineering at Epic Games. All right, so when we set out to make LEGO Fortnite, we had a number of goals that we wanted to accomplish. At a high level, we wanted to create a survival crafting game in a physics sandbox, where the physics sandbox was one of our differentiating factors compared to other offerings in the genre. Now, to achieve a truly kind of physics sandbox feel, we first wanted to focus on enabling destruction and chaos. One of the core components of LEGO is the ability to build. And anything that you should be able to build, you should also be able to destroy. And in order to be destroyed, we want anything in the world, that could be things like trees or other buildings, to be able to cause that destruction, in addition to being able to be destroyed itself. We wanted to enable sort of destruction fantasies, things like cascading effects. So if you have one building knocking into another building, we should experience destruction from that second building. If you're running up and down those buildings while they're being destroyed and falling down, you should be able to have that experience and continue to interact with all our destructible assets in a fully interactive manner. Another thing we wanted to enable is the ability to move your buildings and your structures that you create throughout LEGO Fortnite throughout the world. And like with destruction, we wanted this to apply to absolutely everything in your world. You should be able to move anything that exists in your LEGO Fortnite experience. Once we have a world where we can move everything in, we need to consider how a character is going to interact with that world. There are many different mechanisms to do so. That can be applying forces to physics objects, making damage through various weapons or items, as well as allowing the character to push objects throughout the world. Another core pillar that we wanted to include was a concept of physics items. Items can be any construct that a player uses to impart a change to their physics world. So examples of this include things like thrusters or balloons, which apply forces to an object. It can also be things like barrels or dynamite, which impart strain to an object and cause destruction. We also wanted to address how physics can be enabled as part of building, which led to creation of the dynamic platform concept to enable live physics during the course of building LEGO items. So starting with a core concept of destruction and chaos, we had to solve a number of problems that are a little bit different than the way that we've kind of shipped games before. So if you look at a game like Fortnite Battle Royale, we assume that effectively all of our assets are static meshes and static objects that don't move throughout the world. With destruction as a goal, we had to shift to using geometry collections as our core type of asset. We also had to introduce procedural setups that allow us to scale how these assets are set up to huge numbers of objects. To reach the most number of users, we also wanted to make a game that could scale from low-end platforms all the way to high-end platforms while having the exact same gameplay experience on all of them. Finally, we used a client-server model. So we had to determine what amount of physics runs on the client, what amount of physics runs on the server, and how do we reconcile those two worlds. The first core aspect of everything we did was built around geometry collection assets. Geometry collections were first introduced as part of the chaos destruction system a number of years ago. And they provide a balance between the capabilities of what we call a static mesh and what we call a skeletal mesh. So if you want many different pieces that can all simulate at the same time, that gets very expensive using many different static meshes. Skeletal meshes, which are primarily used for character setups, are fairly heavy if we just want to effectively rigidly move each of the individual aspects of it. So we introduced geometry collections as a way to have a middle ground between those two, allowing us to have a single actor and a single component that comprises many different physics bodies while still being lightweight enough to support effectively, not unlimited, but a fairly large number of individual pieces in the geometry collection. So here's a case of some of the assets that we created as part of LEGO Fortnite. With geometry collections, we introduced a concept of levels. So here, and with many of our sort of LEGO assets that we built, we use 3 different levels. So the green asset is our level 0, which is effectively equivalent to a static mesh. It is as cheap to render and simulate as a single static mesh, while being able to break apart into more individual elements. At the sort of finest level, we have level 2, where we take each of our individual LEGO elements, and each of those can be simulated independently. We also created a level in between, which is our level 1 asset, where we start combining each of those individual elements together to create a still destructible, but not as costly version of the geometry collection. So one of the problems I mentioned was effectively how do we do this at scale? We had hundreds or thousands of assets that we had to effectively make destructible, and we couldn't have our team go through and create all of those assets individually. We also had to make sure that we're effectively using a non-destructive workflow. So if we start making changes to those assets or changes to how we set these things up, we can just procedurally go through and effectively update all of those assets. So here we show kind of what this process looks like. We start with the LEGO database. We then use our importer to ingest all of those objects. We then create 2 different representations of that object. So one is taking all those LEGO elements and combining them together as the basis of our geometry collection. The other is to effectively create a static mesh representation, which we can use for rendering and when nothing is being destroyed, giving us a fairly cheap version of what we're doing. We can combine those 2 assets together into a placeable blueprint, and then we can use this as the asset throughout all of our worlds. Now, as part of this graph, we can also create a number of parts of the geometry collection setup itself. So that level 1 structure that we just looked at on the previous slide, that can be automatically generated procedurally as part of the data flow ingestion path. We can also automatically set up various properties, such as the mass of an object, the friction, as well as things like strain thresholds and how much damage you're allowed to take. Kind of all those properties can be automatically set up for every geometry collection asset that we create in our world. Once we have all the assets in the world, we can look at building them into larger structures. So to do this, we had to create the notion of what we call a connectivity graph. So a connectivity graph is a non-directed graph that we use to glue all of our prefabs together. And then this determines how we effectively simulate any individual group of objects. Another notion that we had to introduce as part of the work we did for LEGO Fortnite was the concept of world supported. So what world supported means from a physics standpoint is effectively we don't simulate that thing. It means, conceptually, it means when you're attached to the ground, you expect your object to effectively be anchored or placed to the ground. And we can then propagate that world-supported mechanism throughout our connectivity graph to make sure your entire object is staying still until it is detached. So in the bottom figure, you can see kind of an example of that, where we build this large structure where each of the nodes in the structure correspond to prefabs, each of the edges in the structure correspond to how they are glued together through the building system. And then once we break kind of that bottom object, that deletes sort of the anchoring or the world-supported nature of it, and it can start tumbling down the hill. We also have to be able to update our connectivity graph when we break things apart into multiple pieces that we still want simulating and we still want gameplay affecting. So the top image shows an example of that. We have a couple different dynamic platforms that are placed together, and then we break one in the center, and this gives us 2 different platforms that we can simulate independently. And as a result, we have 2 different connectivity graphs. So in addition to the connectivity graph, we had to introduce a way for the physics system to actually simulate all these groups as a single unit. That allows us to maximize our performance and support as many of these as we possibly can. So we created something that is known as cluster unions. Cluster unions are a little bit conceptually similar to what welding is to static meshes. So we use the connectivity graph, which defines how many of these things correspond to like a single building or a single construct that's created. We then start aggregating physics properties like collision shapes, mass, inertia, and anything else that defines kind of how that object behaves dynamically. And then we simulate that all as a single object. So the fact that we can basically use a single physics body from a sort of physics engine standpoint for large buildings moving throughout the world allows us to have a very efficient solution to large amounts of simulation. In addition to be able to kind of break buildings in half and like take roofs off of things and be able to use those roofs as basis for vehicles or further kind of building constructs, we wanted to increase the level of visual fidelity that we allowed. So by default, most things that we place tend to be fairly square in nature. So if we simply allow you to sort of break one of the things that you place as a unit, we couldn't do things like have a boulder rolling down a hill and have that create a circular hole. Instead, it would blow through kind of one of your objects and create a square hole. So in order to achieve that kind of look, we extend the notion of our connectivity graph a little further down in that hierarchy. So I mentioned we kind of have level 0, level 1, and level 2. We can take that connectivity information and we can propagate that down into our level 1 children of our parent. So if you have an object that's attached to a prefab next to it, it can have connectivity from that individual object. And then when that entire unit is destroyed, we can then create that circular hole, and those pieces that have that connectivity that's anchoring it to objects that are placed next to it can persist until they are broken apart at a later time. Thus far, we've talked a lot about how we simulate for destruction and chaos. And this introduces a lot of new technology that we can use to do this, but a crucial important of this is it has to be performant on all platforms. And the reason for that, of course, it's a core tenet that all these things are gameplay affecting, and characters on any of these platforms can interact with all of these things. So one of the first major issues we had to address was how do we render at scale on low-end platforms. While geometry collection is certainly able to render much more efficiently than the traditional static mesh approaches for every individual unit, it's not efficient enough to render hundreds or potentially even many hundreds of prefabs and still maintain performance. So one of the reasons for this is the existing geometry collection algorithm was built largely with the notion of fracturing. So in a typical destruction workflow, you start with a single object, you break it up into many different pieces, you effectively glue those pieces together through the geometry collection system, and then each of those pieces break apart. So what that gives you is when you break that apart, you typically have fairly unique pieces at that point. But with LEGO Fortnite, we did things quite differently, because we had all of our individual elements as our starting points, and when we trigger something like destruction, we break things down into those individual elements. So this gives us a couple of opportunities that we can use to optimize performance. The first is to make much more heavy use of instance static meshes. So there's an example on the slide where we have two different lamps. Those lamps are comprised of a number of different geometry collections, or a number of different pieces within geometry collections. So here we have 7 different pieces, where some of the pieces are used by our first geometry collection, some of the pieces are used by our second geometry collection. So when these two geometry collections break apart, we can start treating all of those individual pieces as they break apart from all our different geometry collections as instanced, and that gives us significant performance benefits over our previous system. Another thing that we did rely on was the sort of assumption that, for the most part, most of the objects are not going to be destroying kind of all at the same time. And so as a result, we can optimize the rendering representation for the case where we are not being destroyed. So I mentioned in the data flow side that we created a static mesh. That static mesh, which we call the root proxy, is what we use for rendering until any destruction happens. And then we fail to kind of the instancing case once destruction happens. And those two things combined allows us to render large amounts of geometry collections at scale, even on low-end platforms. So another key component of LEGO Fortnite is running on low-end platforms in terms of memory. So, a number of different devices that we ship on tend to not have a huge amount of memory that we can work with. And if we started incorporating all of the physics data and on every individual LEGO element, we'd start running out of memory extremely quickly. So we did many different things to try to address this. The first is we don't typically allow for full simulation of every individual element. We allow more on that level 1 cluster. And what that effectively gives us is we can delete a lot of the physics representation for the most fine-grained level of granularity. We also did a lot of more brute force kind of optimization, making sure that everything used minimal precision to the extent it was possible, making sure everything was combined into compact bit arrays, things kind of like that. And we got quite a bit of performance improvement just kind of being very aggressive about our data storage throughout kind of the geometry collection construct. Those alone were not really enough to still give us the memory profile that we wanted. And so we took a little bit more of a heavy-handed approach. And when something is not destroyed, we don't store any of the physics representation for anything that can be destroyed. And what we do instead is we generate that physics information at runtime. So that means that we're not paying any more than we would pay as if this was a single static mesh object until the point where it gets destroyed. And then we start creating the physics data that we need to run the simulations. So another major area we wanted to focus on to improve performance was collision. So as probably many of you are aware, collision is generally one of the bigger bottlenecks when it comes to physics performance. So what we want is large, simple shapes. And that allows us to get to a point where we can simulate tens of thousands of these kind of at any given time. However, it's not quite as simple as saying, let's just kind of throw a box around everything, because that has knock-on effects everywhere. So the example kind of on the top here kind of shows a bit of an extreme case of the type of behavior that we want to support. We have a lot of these like thin railings, large openings that we want characters to be able to navigate through. We also want to be able to build effectively on each of these pieces. So to do this, we effectively created two different representations. We created our physics representation, which is quite simple and works in all of our physics kind of use cases when things are moving throughout the world. And then we created a representation that we use for character movement and for building. That is definitely much more fine-grained, but isn't processed by the physics system. And remember, we're relying everything on our procedural-based data flow kind of nodes. So all these things can be procedurally generated and updated as necessary. So here's an example of one of the ways that we kind of generate our collision. So what we do is we start with our individual LEGO elements. We merge them together to form clusters of elements. And then we generate our simplified root collision. In order to prevent these things from, say, covering that door hole, we created something that we called shape protection. So this creates these large spheres that you see kind of in the space. Looks like the video is having a little bit of trouble. But yeah, you can see the large spheres kind of through the door. And then we make sure that any convexes generated do not cross into that space. Now, even with kind of this collision optimization, we wanted to take it further. One of the things that you can start looking at from a physics standpoint is under what situations do you need what granularity of collision? So if you have something, say, rolling across the ground, you want it to behave like the object actually would. You don't want, effectively phantom collisions or things kind of floating above the ground or, problems like that. So you need a somewhat fine-grained representation, although it still can be significantly coarser than what you would use for, say, character movement. But if you're doing things like large-scale destruction and stuff is just kind of flying everywhere, you don't really need that fine-grained of a representation. So what we did is we created a system that we could use at runtime to dynamically generate collision for the situation that we were in. So you can see kind of in this example, we have three different examples of how this collision is generated. We have the top example, which is something we might use for things like character movement. We have kind of the middle example, and you can see some approximations here. You can see kind of the corners being cut to create simpler convexes. And we can use this for kind of most of our physics representation. And then we have kind of the bottom image where we just kind of brute forced as simple possible of a thing we can to represent this particular structure. And we can actually use this in a lot of cases. We can use it kind of when something is flying through the world or when something is effectively being destroyed. Now, one thing to keep in mind is each of these structures are built out of a number of different geometry collection objects. But remember, we have all of the information from the connectivity graph as to how these things are glued together. And because all this collision generation, or because all this collision is generated at runtime, we can dynamically, effectively merge collision across different geometry collections that are part of that cluster union. And this gives us a lot of flexibility to simplify things very aggressively. So another major element in the use of LEGO Fortnite is the event system. So events are used for things like audio or effects, and there are a couple events that we rely very heavily on throughout LEGO Fortnite and really throughout most of our destruction applications. The biggest ones are probably the break events, the removal events, and the collision events. So what these events are pretty much what they sound like. A break event happens when an object breaks apart. A removal event happens when the object gets removed from the world. And a collision event happens when you collide two objects together. Now, at the scale that we're effectively running destruction and simulation in LEGO Fortnite, this creates some problems, because we're essentially processing hundreds of these things at any given frame based on the amount of collisions or breaks that we have happen. So there are two problems with that. One is performance, and one is essentially equality. So if you're hearing 100 collisions at the same time, that's not a very good experience. So we created a completely new system to try to address this. And this allows you to pool events together and to apply large operations on any individual pool of events. And you can use whatever criteria you want to create these pool of events. So some examples of criteria used, which was position. So if objects are in the same area in space, they can use, say, a single sound for all the collisions they do. We also use things like mass. So if you have like a bunch of heavy objects colliding and a bunch of light objects colliding at the same time, we can say do one thing for the light objects and one thing for the heavy objects, but not necessarily do hundreds of things for each of those groups. And this gives us a system that is both efficient, so we can process these things significantly more efficiently than anything we've been able to do before, and gives a lot of control to, say, our audio team or an effects team to create exactly the type of experience that they want. Now, despite all of these systems, LEGO Fortnite is, at its core, a building game. And you can build quite a bit. And it's always going to be possible to do large amounts of destruction in the space. And especially when you're talking about things like low-end platforms, you're probably not going to maintain a steady frame rate doing this. However, we didn't want to take a heavy-handed approach where we explicitly limit how much of this we allowed to happen. So instead, what we wanted to do is we wanted to allow for a smooth player experience, but allow effectively them to do whatever they want from a destruction standpoint and just kind of accept the results that maybe it's going to go a little slower. One of the features that we have with our physics system in Unreal is the ability to tick physics asynchronously. So this means that when player input is processed or when characters are moved, that happens on one thread, while physics is ticking on a completely separate thread. So even if physics is ticking at an extremely low rate, you'll still be able to effectively move throughout the world. Of course, you have to be a little bit careful about how you do this. So if you say let's go to a completely extreme case and say we take a 1-second tick or something like that within the physics system. Meanwhile, we're taking continuous ticks in sort of the game systems. When we get to the point where those two things align again, their timelines are going to be completely off. So one solution to this is you can take basically larger and larger ticks on the physics thread to try to catch up. But this can also lead to a bit of a spiral of death. And if you take too large of a ticks, you can also start introducing instabilities into the physics system. So what we instead did is we created a system that effectively allows you to drop frames. So it'll effectively take that tick, but take it without actually running physics, and use that to catch up. Another thing that we introduced to allow for a bit more realistic results is the concept of extrapolation. So typically when we do synchronization between the game thread and the physics thread, we take the previous frame, we take the next frame, and we interpolate between the two based on where the game thread is in time. Now, if we have super expensive physics, we're not going to have that next frame. So what we can do instead is we can start extrapolating from the position and velocity that we have at the previous frame. All right, now we have a fully destructible world that can run at performance on all the platforms that we want to ship on. And that's quite an achievement kind of in itself. But there are other things that we effectively want to support that have problems that have their own problems that we have to deal with. One is effectively moving arbitrarily far across the map. So this has a lot of complexity when it comes to loading and unloading, and how do you effectively deal with that. Another problem we have is you can build larger and larger these structures. So these can have an increasing number of actors and components in the system, and this can be very detrimental for performance. Finally, we need ways to directly interact through things like forces, strains, and damage. And all of this has to work in a fully networked environment. All right, so at its core, anything can move. And in LEGO Fortnite, we use essentially the world partition system from Unreal for both client and server streaming. So this is done through effectively having a tile-based world. And then every time you have an actor, it's associated with that particular tile. And then every time a tile unloads, it effectively despawns those actors. And when a new tile loads, it spawns the actor associated with that tile. So when we build something, it's attached to the particular tile that you built it on. Now the problem here, of course, is I can build something that looks kind of like a vehicle, shoot it across the map, and then if I'm, say, standing on it, I'm moving across the map, that tile then unloads, and my thing I'm standing on unloads with it. So we need to be able to solve that kind of problems. I mentioned actors and components as a problem that we had to deal with. And ultimately, there's going to be an inherent cost with updating an actors transform, updating a components transform. So we had to be very careful to minimize the amount of that kind of as much as we possibly could. Another complexity is with what we call our persistence system. So persistence is effectively the system that stores a user-created world and all of the data associated with it, and then can load it back in and save it out when sort of a user exits the world and can load it back in. Now the potential issue here is, as with kind of streaming systems and most systems kind of in Unreal, loading order is never guaranteed. So it's very easy to have a case where, say, you have your physics object, it loads in, you load your persistence system, which says, OK, well, the state I was in was I was simulating, so I should start simulating. The ground has not loaded in, and so you start just falling all the way down. So we have to be able to address this kind of situation as well. So I mentioned moving between tiles as kind of a core problem. So the system that we introduced to try to address this is what we call PlaceBased Migration. So unfortunately, it's not as simple as you would hope it would be to, say, take an actor and move it between tiles. So what we ended up having to do is we created a system that would effectively delete an actor when something got a little too far where it was in danger of unloading, recreate that same actor kind of on the tile that was much more closer to where you actually were, so that when the old tile unloaded, you would still have that thing effectively there. Now, this system does get fairly complicated because you can't necessarily guarantee that you can do this in a single frame and maintain performance. So this has to be time sliced across many different frames. And that can lead to potential synchronization problems and other issues as you're sort of creating part of these actors and destroying part of these actors. At the same time, you have to make sure they're part of effectively the same cluster union and the same simulation object that's going through the world. This is an area where this kind of works fairly well, and in the vast majority of cases, but it's also an area we want to continue to improving on, or we want to continue to improve on and support things like, say, moving actors between tiles. Another key component is we don't want to necessarily trigger destruction in the same way. So one of the core tenets throughout the system was we should make everything rule-based. We should make it such that everything we put in the world is still going to work as we put more and more constructs in the world. And the reason for that is we wanted to make sure that we could continue to support LEGO Fortnite as a live experience that would continually evolve. So from a destruction standpoint, in order to do that, we created essentially a notion of a more complicated version of what would typically be a physical material. And this allows us to do things like wood should be lighter, concrete and marble should be heavier, and different amounts of destruction can affect those things in different ways. And I'm going to come back to data flow again, because that effectively allows us to automatically set up all of those properties based on the type of structure that we want. Excuse me. So what we do in this particular case is we use the allowed strain, we use the damage threshold, and we use more traditional properties such as friction or restitution to set up any individual material for any individual assets that's placed, giving us the different types of effects that you see on screen. Another important aspect of the system is we had to be able to support effectively different materials as part of the same structure. So like in the house that we see here, the bottom is significantly weaker than the roof, and we wanted to be able to support that. So we had to make sure that kind of these material properties could be applied on an individual prefab basis. So in addition to effectively making rule-based structure setup, we need to ensure that everything is damageable and destructible. And again, we needed to try to do this as rule-based as possible. So say we introduce new buildings, new constructs, we introduce new weapons and kind of all these things in the future, we want to be able to just set that one thing up and have it work with everything else in the world. So I mentioned before that the destruction system is built around the notion of strain and forces applying strain. So once you apply enough force or enough strain that exceeds the allowable strain in the system, that causes pieces to break apart. This allows you to do things like create weak points in a structure that are more likely to break than others. So we started using this system, which was a pretty large departure from the existing damage system we had, which was grounded in sort of the Fortnite Battle Royale world. So in Battle Royale, you have a very simple system that has weapons have numbers, buildings have health, you do a subtraction, and you destroy the thing when the subtraction goes through. But that's not very grounded in sort of physics and reality. And so we moved to kind of this strain-based system. Now, that works super well when we have all these individual pieces and these stranges between these individual LEGO elements throughout our world. But we also had to figure out how do we deal with trees, how do we deal with boulders, how do we deal with kind of all the other aspects in our world. So what we did here is we effectively created an artificial graph through kind of the static objects that allows us to emulate that kind of strain-based structure, and then we can destroy in effectively the same way. So we have very straightforward applications of strain through things like barrels and dynamite. And then we have other aspects that apply strains, things like a sword or an axe, that can generate an amount of strain that they impart through the system at the contact that they hit the object with. So let's talk about characters for a little bit. Characters are an extremely important part of the user experience, and we need to make sure they have fluid interactions with physics and destruction in our environment. Once pieces are destroyed, we want to make sure that they don't necessarily get in the way, but they're still part of the experience, so players can freely interact with them and move with them. So to do this, we created a debris system. And the debris system treats all of these individual objects, once they're destroyed, a little bit differently than a standard physics object. First core goal is we wanted to make sure that when something is marked as debris, it shouldn't get in the way of the player. So player movement should effectively completely ignore it. And we do this by taking effectively our query system, and any results that the query system would return that include any of these debris, we simply kind of delete those from the results. That allows the character to be completely unencumbered by anything marked as debris. Inside the physics system, we also need debris is slightly different. So if you have a debris piece of physics interacting with a non-debris piece of physics, we change the collision calculations such that the thing marked as debris is effectively infinitely light compared to the thing that's not marked as debris. So it will just freely kind of push the thing out of the way. The system solves the goal of giving us sort of interactive physics, but not getting in the way of the character. One of the benefits that this system provides is effectively none of these individual small pieces are gameplay affecting anymore. So this means that we can reduce our network bandwidth, and we can not send any of the data from these individual pieces over the network, and we can even go as far as basically saying none of this gets simulated on server, which effectively reduces our server costs. Another aspect of character interaction that we wanted to be able to support was more two-way coupled-like interactions between characters and physics objects. So ideally, the way we do this is we use something like the physics-based character movement system, which we're releasing as experimental in 5.4. However, that system was not fully in place when we kind of launched LEGO Fortnite, so we had to come up with a different solution. So in UE, the character movement system is capsule-based and has an infinite mass on that capsule. So there are two ways that characters typically would interact with physics objects. One is the query system that the character movement system uses, keeps a level of separation between the character and the objects. And so as far as physics is concerned, these things are never touching each other. That allows characters to, say, ride on a platform or something like that, but doesn't allow any forces imparted from the character to, say, the platform. The other historical way would be through collision. So you can obviously compute context between the capsule that represents the character and any physics body. The problem with this, of course, is when that capsule is infinitely massive, you could say, take this particular example shown here, apply nearly infinite force from any of your balloons that you add here, and you'd still keep going down because nothing can effectively collide and move that capsule upwards. So instead, we created a fairly bespoke system for just this particular solution. And what we did here is, through the collision callback system that the physics engine supports, we basically compute the context between that capsule and, say, this particular platform. We tell the physics system to completely ignore computing the results of that collision. Instead, we basically apply a downward force at that point. It's not necessarily downward, but in this example, it's downward. And so what you get is results like you see in these two videos right here, where you can get kind of characters walking along a platform, and it starts kind of moving based on the weight of the character, which is exactly kind of what we wanted to achieve. We also introduced a completely new buoyancy system that can scale to objects of any size, shape, mass, and density, which was important to be able to create a wide range of boat-like structures. So to achieve this, we compute two primary properties to figure out how we're going to apply buoyancy to an object. The first is the center of mass of the object, and the second is the submerged volume of an object. So what we can start with is a super simple representation. We can just stick a bounding box around the entire thing. We can compute how much of that bounding box is underwater, and that determines how much force we apply. And then we already have the center of mass from the simulating kind of physics object, and then we apply that buoyancy force kind of at that center of mass. This does obviously have some limitations. So the more non-box-like your structures start to look, the more poor of an approximation this is. So what we did is we introduced the idea of subdividing that box into smaller and smaller boxes as we get things that are very poor approximations to sort of that initial box. This is a system that we only use at runtime and only use when necessary. So it's fairly cheap and gives us a more accurate view of how much volume is submerged. We can also use the surface or use the volume to create an approximate surface area. And we can use that approximate surface area to apply things like drag forces that vary based on artist-tuned currents and things like that through the water that exists in the world. We also need a new networking model to be able to support the idea of an open world physics sandbox. So you can see kind of as it's playing in the video on the bottom right, that was effectively what we started with. That was the system that currently, say, Battle Royale uses for kind of networking physics objects. And it's very simple. It just corrects something very forcibly when there's a difference between client and server. And doesn't make any attempt to correct timelines or kind of anything like that to try to prevent the problem in the future. What we introduced was effectively a new correction system that we call Predictive Interpolation. And we'll go into exactly what that does in a minute, but you can see kind of the difference in behavior that you get once you enable the Predictive Interpolation system. So another part of networking we had to do is figure out exactly which types of structures are going to be networked in which specific ways. So destruction is an example that we can start with. When you have something that's destroyed, we can run that on server, we can run that on client, we can run it on both and do a correction. So the standard default answer is you run it on both and do a correction. However, it's very easy to encounter cases with destruction where, on server I destroy the left side, on client I destroy the right side, and now how do I apply a correction between those two? The only way you can really do that is start like gluing the thing back together and destroying it, which is a really kind of jarring experience. So what we do instead for destruction is we basically don't run on the client at all. We only run at server, and on the client, you can't destroy anything. So the destruction only comes from effectively what happens on the server, and then that gets replicated down to the client, seeing what that looks like. So this can lead to cascading effects and problems with other aspects in the world. So if we have, say, a physically simulated object that actually does do client prediction, and then how does that interact with something that's effectively non-destructible? So an easy example of this is we have a boulder rolling down a hill. The boulder hits the thing that's non-destructible, it stops. On the server, it hits the thing, it goes through. Then we apply a correction to that boulder, and the destruction event happens. So we get this effect of you roll down the hill, you stop, hole forms, and you start going through. It's not completely terrible, but not exactly what we'd want to see either. One easy solution is, well, let's make the boulder so that it only runs on the server. So that would work, but now what happens when my character wants to push a boulder? So you could take this even further and say, well, now I want my character to only run on the server. Well, now you're dealing with large input latency at that point, though, and so we don't want to go down that extreme. So what we do is we do kind of a hybrid approach, and we start transitioning things in the middle. So we start with character must be client prediction. The character must be client predicted. Things character is pushing must be client predicted. And then in our predictive interpolation replication system, we actually kind of correct in the past so that the server is effectively ahead of the client. So when that boulder kind of goes through, that destruction event has effectively already happened. So I'm going to go into a little more detail of the predictive interpolation system, which is now released in UE 5.4. So here we have an object. We have the sort of, the colors are a little bit off, so apologies if I say the wrong color. But we have the purple object kind of in the right, which is the current client version. And then we have the blue object, which is the target version. We first compute the positional differences between the states, which is our vector shown in white in the first slide. We then convert this difference into a velocity by dividing by effectively the round trip time between the client and server. So that gives us the vector shown in pink. We can then get the difference in the two velocities of the object, which is our red vector in the third slide, or the third figure. We can then add the positional difference, giving our target in orange. We then reduce the value based on how much we do apply in a particular frame. So ideally, we don't want to apply a huge correction, because that tends to be fairly jarring for the character. So you can customize how many frames you want that correction to be applied over. And so that gives us the vector shown in orange. And then finally, we basically add that vector on to effectively get our new velocity, which we're applying to the character, which is our green vector kind of in the last figure. All right, so thus far, we focused on having our characters and buildings that can be destroyed, and scaling this to a wide variety of platforms. We also wanted to start providing players with more ways to interact with the physics world, and so we do this through physics items. So the core goal here is, again, we want to get emergent behavior, so we want to give players as many ways as possible to start playing with the physics of the world and creating their own fun experiences. So the first thing we started with was the concept of a thruster. This was quite simple from a physics standpoint. You just kind of have something that sticks on the back that applies a force in a direction. It did provide, it was one of our first toys, or our first items, and it provided a pretty good test case for uncovering a lot of the problems that we talked about how things move through the world, unloading, loading, kind of stuff like that as well. We then moved on to barrels. So barrels added a little bit of complexity. At its core, they just kind of explode something. But there's effectively two parameters that we have to play with here. One is the strain that we impart into the system. So remember, strain is effectively how we apply damage. And two is the amount of force it imparts. And so the amount of force doesn't necessarily affect how something breaks apart in this particular case, but affects kind of how the thing explodes once it actually does break apart. So obviously, tuning this can result in pretty drastic differences in behavior. We wanted to give something to players that, conveys that feel of kind of destruction and chaos, but at the same time doesn't completely tank performance when you're, say, throwing one barrel and kind of making things explode. Of course, you can have many of these and do them all at the same time, and then you can do things like tank your performance more effectively. But at least in the sort of more common cases, we wanted to make sure we had a good balance of performance characteristics and what is most enjoyable for players. Another thing that we launched with was the notion of switches. So switches added kind of a new element, especially in terms of kind of UI, UX, and interaction. What should a player effectively do when it comes to a switch? In this case, we made sort of a fairly simple kind of result that you kind of just build it on, and then you can effectively turn it on and off. And it'll control, in this case, your thrusters as to whether they're moving you forward or not. This gives an added layer of control that players can use to build their constructs. It did introduce a number of interesting questions and challenges, though. So as you can see in this particular example, one of the first kind of obvious questions is, great, so I built something, it's got like multiple thrusters on it, I turn the switch, and it starts shooting me forward, and then I destroyed the thing in the middle, and our connectivity graph updates, and now we have two things. What does the switch do now? The answer to that we took for at least our initial launch was the switch is effectively tied to the thing that it's already on, and then you would have to, say, build a new switch on sort of the other thing that broke apart. There's also an interesting question of the reverse problem. So if you have two individual pieces and you connect them together with a third piece, what does that now do? Does the switch only activate the things that you built it to design for, or does it now activate everything? So the simplest answer is that it's going to activate kind of everything by default. But it still introduces kind of some of the challenges. Balloons kind of were next. They are somewhat similar to thrusters in the fact that they're basically just applying a force. However, there's a different expectation that users have when it comes to lift compared to like a forward thrust. So what you would typically expect if you have a balloon on something is it's not really going to fly up indefinitely. There's some amount of force of effectively air pressure that's going to keep the thing down. However, we don't want to actually pay the cost of trying to simulate air pressure, so we need another solution. So what we did in this particular case is we effectively aggregate what we think the maximum height should be based on the amount of force that you're applying. And then we effectively stop allowing you to apply upward force once you reach that maximum height. And then we dynamically adjust that maximum height based on the number of balloons, the size of the balloons, effectively how much you put onto your platforms or your structures. And then finally, we have wheels. So wheels were a very different construct because they didn't impart some sort of change to one of our cluster unions that we're effectively simulating. Wheels were, in and of themselves, a completely different physics construct that's glued to a cluster union with constraints. So at its core, that sounds fine, but it does introduce a number of fairly interesting problems that we didn't necessarily anticipate when we first went down this path. So one of the examples, I mentioned before that kind of when you load and unload, there's kind of no guarantee of ordering. There's another system that we rely on performance that we call relevancy. So relevancy is when you move too far away, we start unloading objects. So this allows us to maintain performance. But what effectively the problem you have with wheels is it's very easy to build something with a wheel, have the wheel unload, but the rest of it hasn't unloaded yet. And so now it simulates without the wheel. And then when it comes back, say the wheel is under the ground or something like that. So what we did is we introduced kind of a kinematic anchoring system, which is very similar to the system that we actually introduced for loading and unloading as well. So what we do is when something in sort of a physics construct starts to unload, and this could be through just unloading kind of the game or loading the game, but it can also happen through relevancy. So in other words, if we unload this wheel, we turn the rest of the object to kinematic, to not simulating at that point. And then we wait for the entire object to come back into relevancy before we start resimulating that object. So this is a fairly kind of unique system that was designed to handle kind of this specific case. So I also wanted to talk a little bit about some of the more design-oriented challenges. We talked a lot thus far about kind of the technical challenges. Once we start looking at everything is physics and everything is an open world, there's a lot of questions about what should the user be exposed to. So one of the core problems that we had was, what do we do with physics placement? So as you're building something, should these things be simulating? There are trade-offs of kind of making it simulating. So an obvious example is you're trying to build some massive structure, and if it's simulating and constantly falling over, then you're not really going to be able to build that thing. So you could just make everything static. So that works, but now if you're trying to build a crazy vehicle or rocket ship or something like that, you don't actually really know if when you turn physics on at that point, it's actually going to do anything reasonable, or it's just going to fall apart and be destroyed. So we come up, in this particular case, we came up with a little bit of a hybrid approach. We introduced the notion of dynamic platforms. So dynamic platforms are something that you can build upon that are dynamically simulating while you're building. And then we have static platforms, and static platforms effectively don't simulate while you're building. So this kind of allows the user to pick their own trade-offs. And that's one of the design answers we came up with for LEGO Fortnite. An extension of this is something like structural integrity. So think of something like a suspension bridge. There's a lot of kind of engineering that goes into whether a suspension bridge can handle weight when, say, something drives on it. So if we say allow people to design their own suspension bridge and have something drive on it, should the thing kind of collapse under the weight if it's not properly architected? And so for our current version of LEGO Fortnite, we effectively don't do this. So you can create fairly unstructurally safe things, and they'll be fine. But it is kind of a trade-off as to how much you want to expose to users. And finally, one of our bigger problems was effectively the infinite building problem. So I mentioned before memory optimizations. Memory is kind of a core theme with how much can you effectively build. So there's obviously performance concerns. But in the end, if you start violating performance concerns, you just start hurting your frame rate. But it's still kind of playable. If you start running out of memory on your OS, then you start getting crashes. And so you need a much more heavy-handed approach to effectively how do you handle the infinite building problem. And so it is a fairly challenging kind of design question about what do you do. I mentioned before, from a performance standpoint, we just want to maintain player agency, and we allow perf to kind of tank if you're just doing like too much physics from the physics standpoint. But the core question is kind of how do you do that from a memory standpoint? And we don't have a great solution for it, but it's a pretty important kind of design decision to think through. And I hope you can use a lot of the technology that we've released that we developed as part of LEGO Fortnite, released in UE 5.4 to build your own open world kind of sandbox games. We truly believe in the power of emergent gameplay and using physics as a core part of games. Thank everyone for coming to listen to my talk today.